Every day, billions of people turn on a tap and expect water to appear instantly. Most never think about the vast hidden system beneath their streets that makes this possible. Across the United States, Canada, the United Kingdom, Australia, and many other developed countries, much of that infrastructure is decades old. Some sections are over a century old. The future challenge may not be water itself. It may be the aging system responsible for moving it. This network is a massive, silent machine. In the United States alone, the drinking water distribution grid spans approximately 1.9 million kilometers, with more than 90% of these pipes buried underground. The United Kingdom relies on a similarly hidden grid of roughly 250,000 kilometers, with over 95% of its pipes completely out of sight. It is a sprawling web of treatment plants, storage reservoirs, high-pressure pumps, and complex valve systems operating continuously beneath streets and homes. Potable water does not just flow, it is actively cleaned, pressurized, and balanced across varied topographies to reach millions of households simultaneously. Because this infrastructure functions in near total obscurity, its immense scale remains unnoticed by the public. Success is quiet, marked only by the ordinary reliability of a running tap. Yet this unseen grid forms the very foundation of modern urban survival, operating entirely on the premise that it must never stop moving. North America's buried water mains belong to three distinct installation eras: the late 1800s, the industrial push before 1945, and the rapid post-war suburban boom. Today, roughly 20% of these active mains are over 100 years old. Across the continent, more than 1 million miles of pipes are currently approaching or have already exceeded their engineered lifespan. This reliance on legacy hardware is a global pattern, with Victorian-era iron and aging materials remaining in daily service throughout the United Kingdom, continental Europe, and Australia. The vulnerability stems from a fundamental mismatch in design. Municipal systems carry the outdated engineering assumptions of much smaller, less dense communities. Modern cities now stack millions of residents, commercial hubs, and high-pressure demands directly on top of old distribution networks that were never sized for modern urban density. Once treated water enters this aging network, much of it simply vanishes. This is the phenomenon of non-revenue water, potable water that is actively cleaned and pressurized, but leaks directly into the soil before reaching a customer's meter. The World Bank estimates that roughly 30% of global water withdrawals are lost this way. This is an immense daily economic drain happening entirely out of view. In England and Wales, utilities leaked 46.4 liters of water per person every day during the fiscal year 2024 to 2025. In Scotland and Northern Ireland, daily losses reached about 80 liters per person. Even in the highly developed networks of Australia and Europe, non-revenue water averages 25%. For municipal utilities, every lost liter represents wasted treatment chemicals, squandered pumping energy, and lost operating revenue, turning structural decay into a chronic municipal budget crisis. 45% of the global population now lives in cities, a figure projected to reach 2/3 by the year 2050. In North America and Europe, even modest annual urban growth of under 1% adds millions of new residents to municipal grids over a single decade. But urban growth does not stop simply because the pipes beneath the pavement are old. Modern cities operate as massive demand machines, requiring constant volume, pressure stability, and structural redundancy to support high-density residential towers and expanding commercial districts. The underlying distribution networks, however, remain locked in their original, much smaller footprints. As cities densify, utilities are forced to push more water through these same aging, buried assets, subjecting old materials to heavier hydraulic loads and higher velocities. This mismatch transforms a chronic maintenance problem into a fundamental infrastructure constraint. The subterranean network is no longer just a repair challenge. It is beginning to act as a physical ceiling on urban expansion. Climate stress does not create these structural weaknesses, but it aggressively exposes them. Underground networks designed for the predictable weather patterns of the 20th century now face a highly volatile climate. Prolonged droughts lower source water levels, straining pump intake systems, while sudden floods raise groundwater tables and exert massive hydrostatic pressure on buried mains. Intense temperature swings accelerate thermal fatigue in brittle legacy metals. In August 2022, extreme rainfall and flooding overwhelmed Jackson, Mississippi's main treatment plant, leaving 160,000 residents without safe water for weeks as hospitals and schools operated on emergency supplies. When these systems fail, the consequences ripple instantly through local economies. Halfway around the world, the millennium drought from 1997 to 2010 forced Melbourne, Australia, to bypass its failing surface reservoirs entirely, committing the city to a $3.5 billion desalination plant and recycled water schemes. This is the reality of a changing climate. Testing an aging grid, subterranean fragility is forced into the open, demanding expensive, emergency public decisions. Water networks do not fail because city planners forgot they exist. They decay because pipe replacement must compete with highly visible public projects for the same limited pool of funds. Every year, municipal utility managers sit down with capital improvement plans to balance water rates, public debt, and political tolerance. The financial scale of this balancing act is staggering. The Environmental Protection Agency estimates that the United States needs $625 billion over the next 20 years just to maintain its current drinking water infrastructure. Yet the American Water Works Association reports that current spending averages only $33.6 billion annually, leaving a massive deficit as long-term requirements surge to over $2 trillion between 2026 and 2050. This is a global reality. The Organization for Economic Cooperation and Development reports an annual global infrastructure financing gap exceeding $3 trillion, with $400 billion needed specifically for water and sanitation each year. When budgets tighten, the easiest option is postponement. Capital plans from utilities like Toronto Water routinely show deferred pipe replacement projects. It is a quiet, systemic habit, deferring maintenance on invisible pipes to avoid raising visible bills for local ratepayers, even though delayed replacement ultimately multiplies the cost of emergency repairs. Modern water utilities are proving that underground systems can be managed before they break. In the United Kingdom, Severn Trent deployed 400,000 smart meters connected to real-time analytics. This digital grid saved over 6 million liters of water daily by catching silent underground failures early. Instead of waiting for a pipe to rupture and flood a street, operators used advanced metering infrastructure and acoustic sensors to isolate anomalies, cutting leak response times by up to 182 days. Across England and Wales, these tools, combined with active pressure management programs, have steadily reduced pipe bursts. Technology alone does not solve the crisis, but systematic asset management shifts the operational model from reactive patching to predictive repair. By treating buried networks as strategic assets rather than forgotten expenses, cities can stop leaks while they are still small, manageable problems. Most people assume water crises begin when reservoirs run dry and climate conditions fail. Yet the more immediate threat to modern cities is the buried grid of pipes that moves treated water every single day. Because this network functions entirely out of sight, political attention arrives late, usually only after a catastrophic main break floods a neighborhood or cuts off supply to a hospital. In municipal governance, success looks like nothing happening, which makes it easy to postpone expensive capital upgrades. But long-term reliability depends on investments made decades before the first crisis headline appears. Ultimately, the cities that remain resilient are those that modernize their hidden networks before failures become obvious. The underlying question for the future of urban life is not whether water exists in nature, but whether a city still has the structural capacity to deliver it. Modern cities cannot grow on decaying foundations. The threat isn't a lack of water, but our inability to move it. As climate pressures mount, ignoring the ground beneath us is no longer an option. Will we rebuild or wait for the collapse? Subscribe for more stories like this. Every crisis begins as a crack, small enough to ignore, until it isn't.